Okay, today, welcome back to ICP. We're going to be discussing force, review, and more. So this is on Canvas. Okay, really at this point, these are our equations. Up, you know, a lot of times we will replace equations that have A's with G's, and then to find the acceleration or to find G, we can say that a lot of times we'll put a G up here instead of A as well. Okay, our first problem here. Math problem. 1,000 kilogram rocket accelerates from 0 meters per second to 100 meters per second, 2.5 seconds. Find the force acting on the rocket. This is from a couple days ago. Force. Now they're not asking us for weight. So as I look back at my equations, underneath force, I've got a weight equation and I have my other equation for force. They're not asking me for weight, they're asking me to find force. So I'm going to use my equation that says F equals ma. In this case, there's my mass. I don't have an acceleration, but so again, I'm going to have to find acceleration. The equation that we've used from the start on acceleration is right here. Vf equals Vi plus At. So I'm going to use that same equation here to find out what the acceleration is. Vf equals Vi plus At. Rockets start from 0. I don't know the acceleration. The time is 2.5, and they tell me that the final speed is 100 meters per second. Divide both sides by 2.5, and we find out that 40 meters per second squared equals the acceleration. So I can now, that's the acceleration, there's my mass. The force equals 1,000 times 40, or we get an answer to the force equals 40,000 newtons. Okay, now let's talk about Newton's laws. We've covered Newton's first law, we've covered Newton's second law. Newton's first law was all about inertia. All right, at this point, this right here was all about inertia. A great example in Newton's first law says that an object in motion tends to stay in motion. An object in rest tends to stay at rest unless an outside force acts upon it. We talked about an alligator. All right, you could talk about an elephant. You could talk about a rhinoceros. Let's just talk about a car, a red speeding car. We got a car here, it's speeding along. All right, there we go. There's the car. It's speeding along. All right, Newton's first law says that when that car is moving, its natural tendency is to keep moving, and that's why cars can't stop very quickly. That's why there's accidents, because they can't stop on a dime. Their inertia makes them keep moving. Likewise, that's why cars are in accidents quite a bit, because they can't get out of the way. They can't start going fast enough. It's about Newton's second law. All right, Newton's second law is essentially if we apply a force to and a lot of times we use the word object, but we apply a force to a mass, it causes that mass to do what? Causes it to accelerate. And there's where our equation comes from. The force causes a mass to accelerate. An example of this is if I have a nail. Alright, here's my nail. It's in a piece of wood. If we come and hit it, well, when we hit it, we're applying a force. The nail is the mass. And then what happens to the nail? We cause it to gain speed. It goes down, so it accelerates. There's a perfect example of Newton's second law. Hit it with a force, causes the mass of the nail to go downward, so it's gaining speed, so it's accelerating. Projectile motion. Now we haven't talked about projectile motion, but projectile motion is one of the things that helps satellites stay in space due to a falling effect. Here's what I want you to understand. Let's take a look at something. Okay, projectile motion. What we have here is this ball, and we shoot it out, and I've got a picture of the Earth, and I've got this mountain, and we have a cannon up here. And if I shoot this ball and I have a little bit of speed on it, it basically is going to fall down here. What happens is we continue to shoot it faster, it goes farther, but it's still going to fall back to the Earth. Notice we still have this falling effect, and right here I'm shooting it faster. And what would happen if we shot the ball fast enough? If we shot the ball fast enough, it would keep going farther. And if we shot it faster and faster, eventually what would happen is the ball would never be able to fall back because it would get back to where it was. We shoot it fast enough, it'll be back to where it was. Well, that's what a satellite is doing, right? It has this falling effect. It's falling out of orbit. If you think about, they're straight, but it's not going straight. It's bending, and where is it bending back to? It's bending back to the Earth, so it's falling back to the Earth. And this is what causes an object to stay in its orbit. It's falling back to the Earth. It's a delicate combination of speed and gravity. All right. If it goes too fast, all right, it takes off because it's not falling fast. If they shoot it, if they have something going too slow, then it comes back to the Earth and it crashes. So it has to be that right combination of speed and gravity. Our Earth travels around the sun. You got the sun. Likewise, if the Earth goes too fast, we take off and it's going to get real cold. If the Earth were to slow down, likewise, what would happen is we'd come into the sun and we'd burn up. Well, hey, that's all I want to hit you with today. I'll catch you guys on the flip side.